A single server rack at a hyperscale data center draws enough electricity to power a suburban house, continuously. Inside every board in that rack, copper does what it has done since the first transistor was soldered to a circuit. Moves charge, carries signal, holds the entire assembly together. Then a headline arrives saying glass is replacing it. So here's the question I want to answer 3 times. Is copper really finished inside an artificial intelligence chip? A ban or a displacement is never just about the thing that loses. It is more like a lock on a door, and the lock tells you exactly which room someone valued enough to seal. Read what copper is being removed from, and you learn more about the architecture of artificial intelligence hardware than any press release will give you. Is copper really finished inside an artificial intelligence chip? At the substrate level, the evidence leans toward yes, and the evidence is not soft. BOE Technology has demonstrated a glass core substrate reported to reach 20 layers of stacked wiring, a structurally significant threshold for high-density packaging. Reports indicate the substrate cleared thermal cycling and mechanical reliability tests that function as standard gatekeepers before any material earns consideration for production. The physics case is grounded. Glass substrates carry lower dielectric loss than organic laminates, meaning a signal crossing the board surrenders less energy to the material around it. Intel has publicly described glass core substrates as a packaging direction for the second half of this decade. That is a stated roadmap position, not an independent production confirmation, and the difference matters. Think of the substrate as the highway bed and the conductor as the surface on top. Replacing concrete with a new composite underneath does not tell you what is running on the surface. My hypothesis going in was that the claim glass replaces copper was the kind of announcement that sounds dramatic in a press cycle and dissolves under scrutiny. BOE's reliability results made me want to revise that, but only partially. And the partial revision is the interesting part. The substrate is the board the chips sit on. Calling the substrate glass says nothing yet about what is actually conducting current inside it. A house can have concrete walls and still run copper pipe. So ask the question again. Is copper really finished inside an artificial intelligence chip? When you look at function rather than material, copper is still doing most of the work, including inside the glass. Copper-filled vias, meaning vertical pillars drilled and plated into the substrate, are used inside glass core designs to carry current between layers. Glass displaced the organic laminate. Copper did not leave the building. Power delivery, the movement of bulk electrical current from the voltage regulator down to the processor die, remains entirely a copper function. No optical technology carries watts of direct current power at chip scale. Short die-to-die connections, bump contacts, and the interface between the processor and high-bandwidth memory stacks are copper. The bandwidth density requirements at those distances favor electrical over optical at current integration scales. Industry analyst projections, which should be treated as estimates rather than confirmed figures, suggest photonics at the package level carries a cost premium that only makes sense beyond a certain reach. But those figures vary, and no single authoritative threshold has independent verification. I think the industry press is systematically conflating substrate material with interconnect conductor. These are different decisions made at different layers of the package. Treating them as one announcement flattens a story that is actually more precise than the headline. Showing that copper survives in most roles still does not test the claim properly, because power delivery and short links are not where the glass and light argument is being made. To test it honestly, you have to ask the question about the specific distance where the physics argument for replacing copper is actually strongest. Is copper really finished inside an artificial intelligence chip? On the longest, fastest reach from processor to network, across a backplane or between servers, energy per bit finally breaks copper. And this is the one segment where light wins on physics alone. At high data rates over distances measured in centimeters or more, copper electrical links lose signal integrity and require equalizer circuits that themselves consume significant power to compensate. Co-packaged optics, integrating photonic transceivers directly at the chip package edge, eliminate the electrical to optical conversion that currently happens at the module sitting outside the switch or processor. The energy per bit advantage of optical over electrical widens as data rate and reach increase simultaneously. This is not a company claim. It is a consequence of how electromagnetic waves propagate in copper versus how photons travel in glass. Nvidia, Broadcom, and others have co-packaged optics on roadmaps or in early development. Those timelines are company statements, and independent production confirmation is limited as of this writing. BOE's glass substrate work is separately relevant here because low-loss glass is also the waveguide medium for on-package optical routing. In some architectures, the substrate and the optical medium are the same material doing two jobs at once. The distance where optical beats electrical is not the span of a chip. It is roughly the width of your hand. At that scale, the difference in power consumed per gigabit is the difference between a phone charger and a desk lamp, accumulated across tens of thousands of links inside one rack. That scale render is what makes this a real engineering decision rather than a preference. The strongest version of the glass wins argument is not about copper at all. It is about signal integrity at high frequency over distance. That argument is sound. The problem is it has been borrowed and applied to the whole chip, where it does not hold. The most compelling bullish case is that glass substrate combined with co-packaged optics represents a genuine architectural shift. If yields improve and cost curves follow the pattern of previous packaging transitions, the timeline to optical dominant interconnect in artificial intelligence clusters could compress faster than current projections suggest. BOE's reliability data, if it holds through full production qualification, is more than a press story. The most compelling bearish case is that yield on glass core substrates at volume is unproven in public data. Glass is more brittle than organic laminates. Handling at scale introduces breakage risk that does not appear in controlled lab reliability tests. No independent benchmark has confirmed the power or signal claims at production volumes. The gap between current glass core demonstrations and the density required for leading-edge artificial intelligence packages is real and has not been closed on any public timeline. Both readings are partly right and aimed at different time horizons. The physics argument for glass and light is sound. The production argument for copper's near-term survival is equally sound. The error is treating a decade-long transition as a binary swap that happened this quarter, which means the question itself was aimed at the wrong target. Is copper really finished inside an artificial intelligence chip assumes a material either survives or gets replaced wholesale. The architecture does not work that way. The actual decision is not about copper. It is about which segment of a signal path gets optimized and when. The better question is this: which specific reach inside an artificial intelligence system has physics finally made copper the wrong choice for? And what does keeping copper everywhere else tell us about the limits of the replacement? One reach, the longest electrical path between processor and network. Everywhere else, copper is not finished. It is locked in, which is a different kind of verdict. My read is that the copper is dead framing is useful shorthand for a photonic sales cycle and a genuinely misleading description of what is happening inside the package. The precision matters because the companies placing bets on full optical replacement are making a different wager than the companies optimizing the hybrid architecture. Both bets cannot pay off on the same timeline. That copper trace on the substrate, still there, still reddish under magnification, still moving power to every die in the stack, is not a legacy holdover. It is the part of the architecture that the new material was designed around. The lock is on one door. Every other door in that rack is still copper, and reading the displacement backward tells you the room they sealed is the one where distance finally gave light the advantage. Glass did not win. It was assigned. If co-packaged optics replace the electrical link between processor and network switch, which company in that supply chain actually captures the margin? The chip designer, the photonics vendor, or the substrate maker? Leave your answer below. If that question interests you, the next video goes one level deeper. Subscribe and turn on notifications so you don't miss it.